I mean, you go to the main repository of the course and then click on the assignment. At the moment, there's only this one. So this here also doesn't work for me if I click on Open Visual Studio, but we saw that last time already. But I think that's maybe related to, I don't know, my operating system. I'm on Arch Linux. Anyway, but if you click here, then, I mean, I think if you do that the first time, it creates it and so on, but we did that last week already. So you are in your personal repo for this specific assignment. And when I clicked here on open, I had the same problem that some of you reported, that it says it has to reauthorize, and when I click reauthorize, it just doesn't do anything. So I ended up removing my organization from Gitpod and then recreating it, and then it worked for me. But in any case, so eventually it worked, and I also had to authorize again in GitHub. So I had to grant access to this. But then if everything works out, then Visual Studio eventually. I mean, the first time it takes a bit because it has to build the container, but because I tried it out earlier today, and now it should be quite fast. It just pulls the container. It doesn't have to rebuild it. So it shouldn't take much longer, I think. Okay. And once that's done, you basically have a Visual Studio Code environment as almost identical to what would happen if you do it locally. I mean, I personally have my Visual Studio Code configured that this thing is on the right-hand side and so on, but probably you can do that here as well if you wanted to. And then you can just get going and, for example, start the REPL. Okay, so that should work. Hopefully, I hope all of you can get that to work. But if you can't, I mean, there's always the option to clone it locally to your machine. I mean, I also showed you last time the result of doing that. So that would be so this folder in my case. And then you can just start Visual Studio locally. And then again, you have two options. I mean, you can open it in container, then you don't have to install GHC or any other tooling. Or I mean, if you have the compiler with the right version installed on your machine, then of course you can also not open it in the container. So there should be like 3 options at least. I mean, in the browser using Gitpod, locally using the container, or locally using everything local, also having GHC installed. So I hope every one of you will get at least one of those working. Okay, are there any questions, or can I start with so let me go back to my example code. And last time I worked locally because there was this problem with stylish Haskell, but I think Robertino fixed that in the meantime. So let's try in the container again. Okay, so far so good. Of course, you only see the effect if I change something and then save. Yeah, this time I don't get any errors, so it seems to work. I mean, what this stylish Haskell does is just it formats the code a bit. So if I now save, then it indents again, and it's quite useful for the imports. But I mean, at the moment we don't have many imports, so only this hiding. Okay, so before I continue with the lecture, do we have any questions? Okay. In that case, let's jump in. So last time, I mean, so this is basically just the purpose of this lecture is twofold: introduce you to some commonly used Haskell types and practice the so-called standard design pattern, how in the vanilla case you would define functions in Haskell. And being a functional language, defining functions is basically all you do when you program Haskell. Okay, and we started with bool, simple data type with two constructors, none of which takes arguments, and defined a couple of functions on bool. And then I introduced maybe, which is called option or something like that in other programming languages. It's a value, I mean, it's maybe A can have an A inside if the just constructor is used, or not, nothing. And it is often, I mean, often if you have this situation, if you have a function that can return a value or not, then in mainstream languages, often you use null for the not case. But that is, of course, a famous source of all sorts of pain and bugs. So in those situations in Haskell, one would typically need to use something like maybe, which is much safer. Okay, and we had one example, this from maybe function. Given an A and a maybe A, if the maybe A is a just, it just takes that A, but if it's a nothing, it takes the first argument. So you can think of that as providing a default value. So if maybe provides an A, you take that, but if not, you take the default value. Okay, we did this. So let's do something else. So let's say you have two maybes, and you want to, the idea is, I mean, you just want one A, and you first try the first one. If an A is in there, you take it, but if not, you try the second one. Of course, both could be nothing, in which case there's nothing you can do. But you try to get your A first from this, and if it's not there, from that. So let me just type that in, or else maybe A, maybe A, okay. Okay, so what were these steps? I mean, we start basically everything blank. And then normally when you to define a function, you would give names to the arguments. So in this case, we have two, so we can call them whatever, X and Y. I personally, for maybe values, I normally call them something like MX and MY, but that's also a matter of taste. It is, I mean, a lot in programming, of course, is convention and history and folklore. I think Haskell programmers tend to pick quite short names for their variables, often things like X and Y and I and J and A, not these long verbose names. But there are exceptions as well, of course. And yeah, it's not a law, but anyway. So now we still can't do anything without having more information about the MX and the Y. So then the advice was in this case to create more equations and split by cases corresponding to the constructors. So we have the just, and here we have two arguments, both are maybe, so we could do that for both the split. So let's start with the MX. So I distinguish those two cases. It doesn't matter in which order, because as I explained last time, just and nothing are not overlapping. Maybe value is either nothing or just, it can't be both. So the order of the equation doesn't matter. If there is an overlap in the patterns, then it would matter, because Haskell always tries from top to bottom. So then there would be a bias for the first. But in this case, it doesn't matter. Okay, and in this case, so as I said, what is this supposed to do? It tries to find an A and return it, first in the one, then in the other. So in this case, it already found the A, namely the X, which I probably could call A. I'm not sure. Let's leave it with X. So in this case, I can just say X is the answer. And in that case, I don't care about the value of the MY at all. So I can just, well, use an underscore there to indicate that I'm not using the value on the right-hand side. Okay, and what do I do in this case? I mean, I could now split on MY if I want to. So say just Y, nothing. And normally we would align. I think the stylish does it automatically. So now I saved and it automatically aligns the equal signs. So now it's easy. I mean, here I found the Y, so I can use that. And here, neither of the two arguments gave me an A, so I have no choice. I have to say nothing. Oh, sorry. And the mistake, of course, the signature is this. Sorry about that. I can't always produce an A. If neither the first nor the second argument have an A, I can't conjure one out of thin air. Right. And now we see that we were a bit overzealous here because, I mean, with the second argument, so if the first is nothing, so for just y, we return just y. For nothing, we return nothing. So I can actually, I don't need the split here. I can just always return the second argument in this case. So if I, now the right. And that's what's on the slides, except the other way around and with other names for the variable. I mean, we can try it out if we like. I mean, in this case, the function is so simple that we probably wouldn't need to, but especially as for beginners, I think it's important to try everything, to always work in the REPL and always permanently check your things. It's one of the nice things about Haskell. Sorry, I'm not in the right folder. So that is very interactive, the development. So as I said twice before already, you don't sit and write hundreds of lines of code and then compile or try to compile. It's basically permanently a dialogue with REPL. Anyway, and now, oh yeah, there was some question on Telegram how to load modules. So there are two. I mean, first of all, you must be the root for. I mean, where I started the REPL must be at the top level folder. So that's the one that contains the Cabal file. In this case, the Cabal file here is this one. And I'm in this folder, in this 03 data types and functions folder. Okay, and at least that's the easiest. I mean, you can also be higher up, but anyway. And now if I want to, I mean, this module is now, there is only one module, so this is like not necessary really. But if I want to specifically load this module into the REPL, there are two different, I mean, possibilities. I mean, one is to, I mean, it's :L or load. And then I can just give the module name. So like this, and that works. Alternatively, I can also give the path, which in my case is, so it's here in the source folder, and the file is called datatypes functions.hs. So I can also give the path that also works for load. One of the two. And as we will see later, often Haskell, larger Haskell projects are structured with several subfolders and subfolders. And there's a one-to-one mapping between file names and paths. So if there's a subfolder, then the name of that subfolder would also be part of the module name. So we will see that later. In that case, you would, of course, also, I mean, you always need the full name of the module. So everything between module and where, that's the name of the module. Anyway, but I wanted to try out the or else. So let's see. So if I have or else, for example, with characters, just X and just Y. It takes the first, the X. It doesn't care whether the second one is something or nothing. But if the first one is nothing, it gives me the second one. And of course, if both are nothing, it gives me nothing. But now it combines because it doesn't know what type. I mean, earlier the compiler knew I was A, the type A was character because it could infer that type. Now, because nothing in nothing tells you what type you're at, so therefore it's complaining now. But I could help the compiler by giving a type annotation. And then this warning gets away. And then it also sees that the type of this is now, again, maybe character. Okay, let's see what's next. Yeah, I'm not sure whether I really have to go through all of that. Maybe I mean, it's always the same. So, okay, but this is maybe, let's do one slowly again, and maybe we can speed up a bit later. It gets boring. So map, sometimes I hate Copilot. Maybe I should switch it off. I don't want to.
Yeah, it says disable completions there.
Yes, I know. Should I do that?
Yes, you can enable the editor. Also, you imported map maybe without wanting to.
Yeah, thank you. Okay, so what's the idea here? I have a function from A to B, and I want to somehow lift the function to function from maybe A to maybe B. That might be a bit difficult to see. I mean, this looks like a, I mean, it is a function with two arguments, one of type A to B, one of type maybe A, but recall that the function error in Haskell is right associative. So that is the same as if I write it like this. And then it's, in this case, a bit easier to see. So one should rather think of it maybe as a function with one argument. I mean, because of currying, that is just a matter of perspective. That takes a function from A to B and lifts it to a function from maybe A to maybe B. So somehow we want to use, in some sense, the same function here to define one here. Let me remove the parentheses again. So how would we do that? So we give names to things. So this function, I call it f, and then maybe a, let's call it mx again. So what now? So now I'm stuck. I mean, what can I do? And the obvious thing is, again, to split cases by constructors. Now, the first argument, the f, is just a function. There are no constructors for functions. So I can't pattern match on the f. I mean, except giving it a name. That's also a pattern, but I can't split that further into cases. I can't inspect the function. I mean, there's not really a reflection where I could open the function and look at it. So that's just that. And so if I want to make progress, I have to split cases here on the mx. So let's do this, same as before. So mx could be a just x, or it could be a nothing. Right. So what can we do in this case? I mean, of course, we just in all cases return nothing to implement something with the signature. But of course, we want, I mean, the interesting thing, so if we can, we want to make use of our function f. So, and we need to produce a b, or maybe b. So we don't know anything about the types a and b. I mean, they could be int or character or double or strings or functions or anything. So how on earth am I supposed to produce a maybe b? Well, the only thing I have at my disposal is this x now. Actually, when I hover over that, it also tells me x is of type A. And I have this f. And the f is of type function from A to B. So there's only one way how I can possibly get a b, namely by applying this function f to that x. So I can do that. And now I have something of type b. And how do I get something of type maybe b? Where I can apply the just constructor to this. Okay. And in this case, in the second case, there's nothing I can do. I mean, there's no way I can produce a just. In order to get a just, I need a b. The only way for me to get a b is to apply f to an a, but I don't have an a because the only potential source of a's would be from this maybe a, but in this case, in the nothing case, there is no a. So there's no possible way how I could produce just b. So the only option in this case I have is to do a nothing. So this is a nice example that often in Haskell, and particularly if you have these polymorphic functions with lots of type arguments, often you have very little choice what you could possibly do. I would say there are only maybe two ways to implement this. I mean, the only choice I had here was to write nothing or just fx. And in this case, I had no choice whatsoever. We will have another lecture where we go into more detail about this. There's also a name for that, parametricity. But it's something interesting that these functions that look difficult to implement because very abstract, all these type variables, they actually make it easier to implement them. Because you have very little information about A and B, nothing. I mean, you just know its types, you don't know anything about them. And that severely restricts the options you have. And that makes it easier because you have fewer opportunities to make mistakes. Okay, and in this case, we look at the F, so we can replace it with an underscore. And now we can try it out. I mean, we can take some function from whatever to whatever. Let's say, it doesn't matter. I want to take different types for A and B. So let's take a Boolean function, something from int to bool. So I think I haven't shown that before. I can also in the REPL define, temporarily define bind names. So define variables basically. Where variable is the wrong word because in Haskell there are no variables. The value of something doesn't change. But so I can, for example, say f is the function greater 10 from int to bool. So we talked about this short version. So that's the function that checks whether, another way to write this is with lambda, or I can also in the REPL do it with an equation. So I could also say this. Now it's complaining. No, it's not. Sorry, I think if I want to do it like that, I have to annotate the X directly, I think. Oh yeah, and then sorry. Never mind that. Okay, this is what I wanted to show you. So I said earlier that in Haskell there are no variables, so names don't change their value. So now I first defined f like this, and now I defined it like that, which seems to contradict what I just said, but it doesn't. This f is basically a different f from that f, so it shadows it. So it creates a new variable with the name f. It doesn't modify the existing one. It basically creates a new variable. Variable is the wrong word. A new binding for f. Anyway, so I have this f. I can try it out. So f3 is false, f10 is false, f11 is true. Fine. So that works as advertised. And now I can try this map maybe. So if I do map maybe just 3. Sorry, f. I forgot the f. Map maybe just 3. It gives me just false. So basically f applied to 3 and then with a just. Same if I have 10, it's just false. If I have just 11, it's just true. But if I apply it to nothing, then I get nothing. So that's exactly what we said. So it's a way to turn a function from A to B into a function from maybe A to maybe B. Okay, let's see what's next. Right, and let me just see. I think these two, I don't do them because it's frankly quite boring. So let's just look at the slides, except if there are questions. So add maybes, the idea is I have two maybe ints and want to produce a maybe int. And if both of the maybe ints are just, so if I have a just x and a just y, then I give back a just of x plus y. So I add x and y. But if the one or the other or both are nothing, I just give nothing. So that's what these two lines say. And maybe I should have, anyway, let's do this one instead. The lift maybe. So lift maybe. So we had this map maybe, takes a function from A to B and lifts it to a function from maybe A to maybe B. So this lift maybe is similar or same idea, but now for functions with two arguments. So we have some function from a to b to c. I want to lift it to a function from maybe a to maybe b to maybe c. And the idea is the same as for this add maybe, and also the same as for this map maybe. So give the function a name. And I want to apply the function, but I can only do that if I get an a and a b. So if this and this is just. So in this case, for just a, if I have a just b, then I can apply my function f to a and b, and all is good. But in all other cases, so if one of the two is a nothing, or both, there's nothing I can apply the f to, so I have a choice but to say nothing. But let's load that. Okay. And this add maybe is actually a special case. So if you look at the slides again, the add maybe is just a special case where this function that we want to lift is addition. So if I do lift maybe of plus, apply to just 42 and just 8, and I must just tell the compiler that this is now int, then it will basically get the 42 and the 8 out of the maybe, add them and wrap them in a maybe, in a just again, give me 50. But if one of the two sides nothing, then I get nothing. Okay, so that was the examples for maybe. And before I move to pairs, are there any questions to maybe? Maybe any questions about maybe?
Not yet.
Okay, so maybe is also, I mean, in last lecture I said that lists are the workhorse of Haskell. And I think almost the same can be said for maybe. So that pops up everywhere. And also almost the same can be said for pairs. So they are also very common. That is another, so we saw this special treatment. I mean, we have seen at very few spots, we have seen special treatment. We saw for Booleans, basically if then else, which could simply be defined as a function as the special if then else syntax. Lists have special syntax that you can easily write down lists. And pairs also have special syntax. So basically I mean, you couldn't write that in your own code like this. That would be in syntax error, but you can think of it like that. So the type is called, I mean, pronounced pair AB. So the idea is it's an A and a B. It's a tuple, a two tuple, a pair, two things, an A and a B. And so the type is called A, B in parentheses, but the constructor also parentheses and a comma between the two. So this is on the right hand side is an I mean, it's the constructor. So you construct the pair putting parentheses around it and a comma between. So if I can do that, for example, I can do, let's say, a Boolean and a character. So I put parentheses around and a comma between. And yeah, that works. And I can ask for the type like always. And it tells me, okay, this is of type pairs, a pair of a Boolean and a character. I'm not sure whether that's on the slides. I mean, in Haskell, we also have like triples and quadruples. So you can also do this. And now you get a triple Boolean character string. And you can continue that, but not, I think it's until, I don't know, 8 or 10 or 11, something like that. But it's normally considered bad practice to use tuples that get too long. So 2 or 3 or maybe 4 are okay, but after that you would probably define a data because then it gets confusing which is which. So this is normally only used for 2 or 3. Okay. So the constructor is this, and actually this is valid syntax. So the constructor is basically the comma. And as I said last time, if you want to change an operator, infix operator into prefix, you can put it in parentheses. So this would also work. I could, I had this true comma C. Alternatively, I could also write this like this. So that's the same thing. But no, I mean, it's somewhat uncommon to do this, but nevertheless, it's legal Haskell. Right, so that's the constructor. And how, I mean, before, I mean, this lecture, all the sections follow the same schema. We introduce a data type and we look at functions operating on this data type, how they are defined. So for Booleans, we said, okay, there are two constructors, true and false. So typically a function on Boolean will have two equations, one for the true case, one for the false case. Then we had maybe two constructors, nothing and just. So typically a function defined maybe will have two equations, one for nothing, one for just. Now, pairs only have one constructor, only the comma constructor. So typically a function defined on pairs will only have one equation. And you better match on the pair. So two like very common functions are first and second that extract the first and the second component from the pair. So first goes from A comma B to A. Okay, and so following this, I mean, we could give the pair a name like whatever, X or XY. But so now we stuck. So we split by cases. There is only one case, but we pattern match on the constructor. So the constructor is this comma thing. So we can do it like this, or maybe this is confusing, or I don't know. I mean, you don't have to call it A and B. You could also call it X and Y. Okay, and in this case, the first is the A. So A. And we see we don't care what the second is, the B. So we can also do an underscore there. And then there is same for second to extract the second component from a pair. And that's not sure whether, I mean, that is, if I now try it out, it will probably not work because, and now it complains that it clashes with something in the prelude because first and second are also in the prelude. So if I want to find my own version, I have to hide it as well. So first of true C gives you true, and second of true C gives you C. Simple enough, I hope. Okay, maybe we don't have to do this. So if you want to swap components, so it's a function from AB to B comma A. And if you pattern match on the pair, you get a pair of A and the B. So the result is a pair of the same B and the same A, but the other way around. Curry, this is more interesting. So maybe I should write that again. I always forget which is which. Okay. We talked about currying in the last lecture already. Okay, so what, I mean, let's first understand what that is. So in this case, it's again helpful to remember that the function arrow is right associative. So this is the same as if it was this. And sorry, no, it's correct. It's correct. Okay, so what's the first thing? That's a function from pairs of an A and a B to C. And the second thing is a function from A to C, what until now we always consider as a function in two arguments, one of type A, one of type B. So this curly function converts a function that operates on pairs of A's and B's into this curried version. That's why it's called curry, A to B, C. So in a function on A's that returns a function on B's that returns C. And this is basically how most other programming languages look at functions into arguments. So they normally don't use this current version, but something like this. And this is how we normally do it in Haskell. But the curry function shows that you can convert between the one and the other version. And the definition is super simple. So so I give a name to the first argument, the f, and I introduce names for the a and the b as well. So now for this is helpful again to remove this again. So you see it's also a function of 3 arguments, this curry. This function, the a and the b. And now what can I do? I need a c. And the only way to get a c is to apply this first function. So no matter what I do, I must apply this first function to something. But to what? Now the editor can also help me. It says I need something of type pair of a and b. I mean, as the signature here of f suggests. Okay, so how do I get a pair of a and b? I mean, I can start slowly and know, I mean, in order to give a pair, I need this pair constructor, the comma. So I can write that already and leave what I write for first and second as holds. And now I see this first one must be of type A, and the second one must be of type B. And actually, if you look more at the helped window here, so it already tells you the types of everything you have in scope. Sorry, I touched my screen. So it already tells you A's of type A. And I think if you scroll down here, it even makes a suggestion. Valid whole fit include A. So I mean, that's not often, it's not helpful, but sometimes it is. So basically the editor tells you what you have to write here and here. So the definition is very, very simple. And then there's also query, which goes the other way around. So this unquery takes a function, a normal Haskell function with 2 arguments, a queried function, and turns it into a function that works on pairs. And again, these parentheses are optional. And that's also one line, of course. So we give a name to the first argument, this function, and a name to, we could give a name to the second one, but then we would immediately pattern match. So we pattern match directly. So we get a pair of an A and a B. And now we must produce a C. The only way we can possibly get a C is using our function f, but we must apply the function f to an A and a B. And as so happens, luckily we have an A and a B lying around, so we can just do it. So that looks very, I mean, if nothing is really happening. And it's also true that query and unquery are inverse to each other. So if I first query and then unquery, or first unquery and then query, then I basically end up with the same function. So it will behave the same. And can we try this? So for example, we can unquery. So let's call it whatever, Java plus Java, or let's just not be nasty. Let's just call it add. So we unquery plus. And let's again restrict this to, I don't know. Sorry, I just want to make sure that that is on int. So I unqueried plus. So now I have a function that operates on pairs. So now I can, for example, say add 3 and 7, and I get 10. And I can, but I mean, yes. And if I now query it again, so if I query add, so now it's like the original plus. So I get a function back, a queried function with 2 arguments. So query and unquery convert between the 2. But in Haskell, we almost exclusively use these queried functions and not the those. But this shows the current uncurrent shows that it's really the same. I mean, it's exactly the same functions. You can convert back and forth between the current and the uncurrent version. Okay, that's that. Right, so that's pairs. Are there any questions to pairs?
Not so far.
Okay. Lists, we have talked about lists already. Let's consider that as a recap. So also special syntax, as we saw. So we have two constructors, the empty list and the non-empty list. Non-empty list is written like this. This colon in this case is often pronounced cons, so for some historical reasons. And the arguments of this cons constructor are normally called head and tail. So the way you think about it is, I mean, so a list is either the empty list or not. And if it's not empty, it has a head, an A at the head, and then a shorter list as its tail. I mean, normally shorter. But as we saw last time already, there are also infinite constructs in Haskell. So this is not necessarily true that this is shorter. But anyway, and we have special, so the constructors are the empty list and this colon, this cons. And the types is, so the empty list is similar to nothing. It's polymorph. So the same symbol is used for empty lists of all element types. And then we have this cons. So given an element and a list, we construct the list where the head is the first element and the second element argument is the tail. So we have done that before. I can, for example, and we also know that strings are lists of characters. So if I cons capital K to the list Enya, then I get Kenya. Now strings I have a somewhat special treatment in Haskell to make it nicer to work with them. So we can of course do the same with Booleans, for example. So I can cons true to first do the empty list. So I get a list with just one element, just true. Now I could cons false to this and whatever, another false. And we also have seen on Wednesday already that there's the special syntax for lists, so you don't have to write the constructors explicitly. You can also use this notation for lists. So brackets and then just list the elements. Right. And now we can follow the same logic again that we did for Boolean, maybe, and pairs. So lists have two constructors, empty lists and cons. So functions defined on list will normally have two equations, one for the empty list case, one for the cons case. And one new interesting thing now with lists is it's the first recursive, I mean, not really, because our chain type was also recursive. But of the classic Haskell function, or of the important not built-in, but standard Haskell types that we look at in this lecture, lists are the first ones that are recursive. So recursive data type means that some constructor argument of at least one of the constructors is the type that we are just defining. So we're defining lists, and one of the constructors, the cons constructor, has an argument which is of the type list, which we are just defining. So definition that uses itself, and that's a recursive definition. And it will turn out that functions on lists for that reason tend to be recursive. So if you define a function fun, then we two constructors, so one equation for the empty list, one for the cons case, and often somewhere in the cons case, in the second equation, we will call the function we are just defining on the tail of the list. And that is, it's often like that in Haskell, that the data types and the functions operating on them sort of mirror or reflect each other. So if you have a recursive data type, then functions on that data type tend to be recursive. Okay, I mean, this is boring, so maybe I can skip that. I mean, length we have seen before also for our chains. Let's see, right. And I think LM we've also seen. So, okay, this, okay, fine. But let's go through it. So, length of a list. So following this standard pattern, we have two cases, one for the empty list and one for the cons case, the non-empty list. So what's the length of the empty list? Well, 0. And what's the length of this thing? A list with head X and tail XS? Well, I have no idea. But if I knew the length of XS, then I also know the length of this thing. It's 1 longer than this. So it's 1 plus and recursively taking the length of tail. And that is the same, almost identical to how we defined the length of a chain in our introductory lecture. Of course, as we saw, chains are more or less the same as lists. Just, I mean, we defined the data type ourselves and gave different names to the constructors and changed the order of two arguments, but morally it's basically the same. So here it's a nice demonstration of this here, how functions on lists look like. One equation for the empty case, one for the non-empty case, for the cons case, and that one tends to be recursive, where the function you are just defining is called on the tail of the list. So what's the length of a list? The empty list, for the empty list it's 0, and for non-empty list, recursively calculate the length of the tail and add 1 for the head. The LM function we also saw in disguise when we had this has block prop function on chains. So given an element of element A and a list of A's, we want to know whether that A is an element of the list. And again, two equations, one for the empty list case, one for the cons case. So if the list is empty, it doesn't matter what X is, it's definitely false. There are no elements, so in particular, none of the elements can be X because there are no elements. So if the list is not empty, we basically have two chances. We can be lucky and the very first element in the list, the head of the list, is already X. So we check that here, X equals Y. In that case, that's good. So then, yes, we found the X. But if they are not the same, we still have the chance that we find the X in the tail. So we also recursively call LMX on the tail of the list. And if one or the other is true, then the whole thing is true. And we also see here we compare for equality between X and Y. So our type A can't be an arbitrary type. It must be in type instance of the eq class, because we need to compare for equality. And then we can try that out if we want. So, I mean, this is all in the prelude, therefore I don't have, and we already talked about that. I think that it's even for foldable, not just for lists. So we can do whatever, lm y Kenya is true, but lm z Kenya is false. And of course, the length of Kenya is 5. Okay. So this is interesting. Maybe I can do that. I think we haven't seen that for lists yet. So plus concatenation. There was a question last lecture about the performance of that. I remember now. So concatenating two lists. And I think, I mean, I'm sure that's also built in. So let's hide that as well. Okay. All this stuff I commented out. Okay. And that's also convention in Haskell norm. I mean, often the name for a list is something, I mean, it's one letter and an S, so X's or Y's. Pronounced X's or Y's. It's also just a convention, but it's very typical that a list is X's. And if you need the second one, then it's Y's, and the third one would be Z's. Okay, so now following standard design pattern, we would split So we can have a choice X's or Y's. Let's start with the X's. So we look at, sorry, let's copy it first. So we split cases, empty list and non-empty list. So what is concatenating the empty list with another list? Well, it's this other list. So that's easy. And now, I mean, maybe here it's not so easy, but from what I said before, we know that these functions that defined on list tend to recursively call themselves on the tail. So somehow we will concatenate the tail, which is called X's in this case, with something. And if you squint a bit, then you see that concatenating this with Y's is the same as first concatenating X's with Y's, and then consing the X at the end. So this is X cons XS concatenated with Y's. So again, the same pattern. We are defining plus plus, and we are recursively calling it in the cons case on the tail. In order to concatenate the list with head X and tail XS with Y, you first concatenate the tail with the Y's and then put the head X in front. And we can, of course, try it out. I hope we can, and it seems to work. And here you can somehow also see this complexity. I mean, if you look about it, if you think about it, so basically you have one recursive call for each element. I mean, because we recurse on the first argument, basically you get one recursive call for each element in the first list. Therefore, I said yes, or day before yesterday when somebody asked that the time complexity is linear in the length of the first list. We don't have the second list, doesn't matter because we never look at it. So because of laziness, we don't have to. I mean, if you actually wanted the result, then obviously it's also linear in the length of the second list. But anyway. Right, so that's that concatenation. Let's just see. Okay, maybe we can complete this and then have a break. So reversal. Right, maybe I don't do this on the slides. Sorry, I do it in the slides. So how do we reverse a list? We, again, the two cases, empty list, non-empty list. So how would I reverse the empty list? Well, that's easy. It's again the empty list. How do I reverse something like this? Well, one way to do it is to, and we know we should probably recursively call the function we're just defining reverse on the tail. So somehow, how does reverse XS help me? If I know I reverse the tail, how can I get the reversal of the whole list? And I mean, this is the thing. I mean, if you think about it, so you have like the list Kenya, and you want to reverse it. So the tail is Enya. So now if you reverse Enya, you get A, Y, and E recursively. So now where does the K go? Well, it goes right at the end. So the K must move at the back of, so you can reverse the tail and then move the K at the back. And that's exactly what it says here. So we reverse the tail and concatenate that with the element that just contains the head. As it turns out, this works. Maybe I should have implemented it. Sorry. No, let me not hide this in this case. Let me just give it a different name. Let's call it reverse prime. So list A to list A. So empty list is empty list, and reverse prime non-empty list is I recursively reverse the tail and then concatenate with the head, the list just containing the head. I can try this out. So I can do reverse prime Nairobi or Kenya. So that works. Nice. However, if I, let me see. So if I take the list, I haven't shown you that yet, but there is another special thing with lists. So you can do something like this to get the list from 1 to 100. So for certain types that are instance of the enum class, you have this dot dot operation. So you give a start element, dot dot end element, and then you get the list of all elements from start to end. There's also, you can also do something like with the comma, and so then you would not get everything between 1 and 100, but only at the distance given by this. And that doesn't only work for integers, it works for everything in the enum class, including characters, for example. So I can do everything from A to Z, and I get the string that contains all capital letters from A to Z. Anyway, I just wanted to do that to be able to get a long list quickly. So let's call let's take 10 million again. 10 million. Set, what was it? Plus S. Yeah, to get this timing information. So length X. Okay, that takes 1 second. So now if I take the length of reverse prime XS, I get a stack overflow. And okay, let's try a shorter one. I don't know why the length takes longer for the shorter one. Never mind. Just want to see whether I can even reverse this with 1 million elements. I should have taken less. And I hope my computer doesn't crash or anything. Okay, but I mean, fine. Takes forever. Let's just be less ambitious, just 10,000, okay? Okay, this is now fast. In case you're wondering why I use the length, I just want to force Haskell to actually evaluate it. And I don't want, okay, now it worked, but it took forever, like 5 seconds. Okay, but there's also the reason I called it prime is because there's also a function built into, not built in, but in the prelude that is called reverse and does that. And if I use the prelude function, it's almost immediately. And with the prelude function, I can also, what was that, 10 million? Yes. So this is the long one again, the 10 million one. And if yeah, so that also works. So in other words, even though this is semantically correct, so it does reverse lists, it's somehow horribly inefficient. And I think that's topic of the second set of assignments, to basically come up with the better version of reverse. That's the one that Prelude uses, and to understand why this is bad. So this basically has quadratic complexity, or maybe it's even in the lecture later. I think it's, yeah, probably. I don't know. I forgot. I know there's something in the assignment as well. In any case, this is basically quadratic complexity in the length of the list, but you only need linear. So this is like an inefficient implementation. So that's okay. And last example, filter. So here the idea is, given a predicate, a function from A to Booleans, and the list of A's, give me back the list of A's that only contains those A's for which the predicate is true. So So filter. I have a predicate on A's and a list of A's and want to only those A's where the predicate is true. So I give a name to the predicate. Let's call it P for predicate and the list. So now, as in this form, I can't do anything. So I follow the standard design pattern on lists. So have standard design patterns, including on standard Haskell design pattern. Right. So in the case of the empty lists, I mean, I only want to keep the elements for which P is true. There is no element to begin with. So obviously the answer is the empty list. There's no other choice. Sorry. Empty list. And in this case, I also don't need the P. So now in case of this, well, it depends, right? I must check whether X head satisfies the predicate or not. So we have seen this guard notation on Wednesday already. So we can check whether the predicate holds for X. And if it does, we do include the X in the result. And otherwise we don't. Okay, but now we have to recursively apply filter P to the tail. Okay, and if P does not hold for X, then we drop X from the result, but still, of course, have to recursively go over the tail. Okay, now for some reason, stylish Haskell is not that stylish. So I would also indent this. And I would indent it the same as in this line. But that's also a matter of taste. I do that. Yes. Okay. And I mean, we can try that out. So for example, filter even 100. Leaves me with just even numbers, and I do filter odd. Left with just the odd numbers, and I can of course also do something like greater 23, and it only gives me the element greater 23. Okay, I think that's the end of this list chapter. So are there any questions?
Not so far.
Okay, then let's have a break until, I don't know, 25.
Yep, sure.
Okay,
Okay, see you.
see you. Thank you. Okay, should we continue, or are there any questions?
No questions in the chat.
Okay. Right, so this is now not, I mean, so what types have we seen now? It was Boolean, maybe pairs and lists, I think. And those are all, I mean, used all the time, all over the place, and part of the prelude and so on. So this type now is not in the prelude. There are like very commonly used libraries that have something like this, but the one we're looking at now is, I mean, nobody would use that in practice, but nevertheless, it's maybe a nice example, hopefully. So the idea is to get a lookup table. So called, I don't know what it's called, but like a map. In some languages, it's called a map. In Python, I think. So the idea is we have two types, K and V, for key and value. And we want to, given a key, be able to store, I mean, key value pairs in the table and do the usual things like insert into the table, look up, given a key, look up the corresponding value if it exists, and also delete from the table again. I'm not sure whether we want to, anyways, that's the idea. And this is a type with two type parameters, so one for keys, one for values. And there are, I mean, different ways to do this. And like normal, I mean, the one I just mentioned in the standard, in one standard library that is actually called map, uses balance binary trees for this. So we will look at the map type in a later lecture. But now we want to keep it simple and just use a list of pairs, a list of key value pairs to store that. So that will have bad performance. So linear, basically in the number of elements in the table, whereas these binary trees can give us logarithmic performance. But nevertheless, so that's the idea. And we could, of course, work with this type directly, but we instead give it a name. So we use this type keyword to give a different name for this. And we want to implement this interface. So we want to have a way to construct the empty table. We want to be able to insert into the table. So given a key and a value and an existing table, we want to get an updated table, which basically contains everything the existing one does. And on top of that, also the new key value pair. We want to be able to delete. So given a key and a table, we want to remove the key K from it. And we want to be able to look up. So given a key and a table, we want to find the corresponding value if it exists. So this is a good opportunity to use the maybe type because, I mean, maybe the key is in the table, maybe it's not. If it's not, then we would return a nothing. And if it is, we would return a just V. And this, in imperative language, in languages you are maybe used to, the signatures would be different because normally they, or I mean, it depends, but normally they would modify, mutate the table. So for example, insert would just get a key and a value and a table and don't return anything. And it would modify the existing table. Same for delete. It would just modify the table. Whereas, but Haskell by default, or normally we use so-called persistent data structures. So we don't mutate in place, even though that's also possible in Haskell. But instead we basically always return a new updated value. And that sounds bad. That sounds as if it would have horrible performance. It sounds as if we would always have to duplicate the whole thing, but that's not the case. So in a later lecture, we'll look at persistent data structures in more detail. And the point is, because everything is immutable, it's safe to share. So in this case, for example, with insert, we wouldn't recreate the whole table. we would basically keep this one and just the new one, the updated one, would share a lot of memory with this one. And that's safe because we can't mutate this one, so it doesn't matter. So this is the interface we want to do. So let's start implementing that. So let's do this. So a table, key value, just list of pairs of Ks and Vs. And let's try to implement the first thing on our list of the interface we want for our table, the API we want for our table, empty. And of course, the empty table will be represented by the empty list, the one that, table AV. So the empty table just is the empty list. Now I get warnings because the REPL doesn't know what types I want to use, so I get rid of these warnings if I say, for example, int character, right? So that's not very exciting. So what next? Insert. So a key and a value and an existing table, and giving us a new table with key and value inserted. So we have a key, we have a value, we have a table. So now we have several choices. I mean, for example, we could check whether the key is already in the table and do something in that case. But we do the simplest thing. We just append the new key value pair in front of the existing table. So with this, I mean, that's a design choice. So that means that we can end up with lists where the same key appears more than once, but that won't be a problem because when we look up, we will always return the first V we find. Basically, this is like we shadow the existing one. I mean, we can try this out. But I mean, this is not, I mean, one could implement that differently, actually, but this is how it's implemented here. So let's reload. So now I can already create tables. I mean, I can, for example, insert 42 X into insert 7 Y empty. So I start with the empty table, I insert key 7 value Y, and then I insert 42 value X, and I end up with this. I mean, I could, for example, insert 7 again, maybe with a different value. And we see this is now this design choice that we don't worry if the key was already present. We just prepend we call the new key value pair at the head of the list. Okay, so far so good. So that means using our API, we can now, I mean, that we have already empty and insert, we can already build these tables. Now, what was next? Delete, I think. Let me just check how they do it here. Right. So delete. So given a key and a table, we return a table again where that key has been deleted. Okay. So now I can't just do it like this. I mean, now I'm stuck. I don't know what to do, what to write. And I don't know anything about case, so the only chance I have is to split cases on table, which I know is lists. So let me do this. So we have the empty list case and the cons list case. Okay. And in the cons case, because our table type has pairs, so we have some key, let's call it key prime, and some value. and the rest of the list. Okay. So what do I do? Well, how do I delete a key from the empty list? The empty table, it's again the empty table. So that case is easy. And in that case, I also don't care about the key. So I can turn it into an underscore. So what in this case? Well, now I must check. There are two things. First of all, I must take care of this k prime. So if that happens to be the same as the k, then I have to remove this key pair. But that's not enough because of this decision we made here, or I made for you, that insert is just prepending. So it's not enough to delete the key once. It could also appear again in the tail. So I must also recursively delete it from the tail. So, but in any case, I must check whether k equals k prime. So I have two cases. Okay, so if k equals k prime, then I will drop this pair here. And what do I do with the x's? Well, I have to recursively delete the key from the x's as well. In this case, I will delete k from x's. And if they are not the same, so then I want to keep the key prime v. And now for the rest, I then recursively delete from the x's. Okay, and now I get an error because I'm using equality. And this is not, I don't know anything about k, so I don't know whether I can compare keys for equality. So I need this constraint that k's can be compared for equality. And now to my disappointment. So stylish Haskell doesn't do that, but I would format it like this. So now we can try this. So we had this example table. So now if I delete, let's first try to delete something, a key that's not there, like 0. So nothing happens and I get the same back. Now let's try to delete 42. And indeed it's been removed. And now let's try to delete the 7, which happens to be in the table twice. And that also works. So we're only left with the 42. So the delete also seems to work nicely. And the final one was lookup. So we want to be able to, the whole point of a lookup table is to look up things. So lookup. So given a key and a table, if the key is in the table, we want the corresponding v, and if not, then not. So we want a maybe value back. Again, but if it's a name and don't know anything about it, there's no way for me to do anything except return nothing, but that's not what I want. I want to look into the table. So again, I will create two cases for the empty list and the one where the cons case. Okay, so in the case of the empty list, then obviously the key is not there. So there's nothing to look up. So I have no choice. I must return nothing. And in this case, well, again, it depends what k prime is. So if k prime happens to be k or not. So if it is, then I'm done. I have found my value, namely the v. And I don't have to look any further. I also don't, I shouldn't look any further because of this design decision we took here with the shadowing. I'm interested in the first value with that key I find. So in this case, I'm done. And I know the answer is just v. Okay. Okay, and in this case, I haven't found it yet. But I only looked at the head. the list, so I still have my chance to find the key in the tail, so I can recursively look up that key in the tail of the list. And okay, that's the prelude. Let's hide it. Okay, now of course I get, because I'm using equality comparison again, same problem as with delete, so I need the E constraint. And I get this warning from my editor that in this case I don't need the K, so that's not an error, but I can replace it with an underscore. Okay, and now let's reload. So if we use our example lookup table again, so if I try to look up something that's not in there, like 0, I get nothing. Okay, it's always complaining because it doesn't know whether it's int or whatever, so I can make those warnings go away when I give a type annotation here. Right, so if the key is not there, it gives me nothing. So now let's try a key that is there, like 42. So it finds the X. And finally, let's try a key that's there more than once. And it gives me the one I inserted last. So that's the correct behavior. So it doesn't give me this Y, it gives me the Q. It works. So we have basically implemented this API. So this table type with, I can construct tables with empty insert. I can modify them again then with delete. And most importantly, of course, I can actually look up stuff. And okay, so that's that. Are there any questions to that?
Not so far.
Right. So what I will do now, I think, is I move that to a different module. So let me call it, I don't know, table, I think, call it, or yeah, whatever. So I just copied this and created a new module. And we'll talk about Cabal files later, so I have to do something here. Don't worry. And now, of course, the name is wrong, so it's table. And let me just delete everything that's related to tables. And here, let me delete everything that's related to tables. And now I'm worried why I don't get a warning. I think it's still. Sometimes when you like add a module or change something in the Cabal file, it takes a while until the editor support picks up again. So I just reload the window and hope it will come back. And as I said on Monday already, I think, I mean, this is relatively new, only for the last, I don't know, 5 years maybe, or 3 years have we had this nice editor support. So before all, I mean, all you had was the REPL basically. So this is pure luxury for me that I can just, the mouse hover somewhere and I get all these nice indications. For some reason, it's still not doing anything. I want the.
I think it's already working, but it doesn't give you any warning.
Yes,
Why
because change
yeah, it's
the
working.
change.
So,
change
so
for
why is
table.
it? Is that related to Copilot? I'm confused. I'm expecting warnings because I'm hiding stuff. Oh yeah, but probably not warnings because it's maybe that doesn't give a warning if you hide stuff that you're not using anyway. So let me just delete everything.
Maybe.
Yeah.
Try it
I
out.
think all is good. So let me just basically delete all the hidings. And now I should get here. Now I get this error again. That lookup is, so I hide that. And now it should be. Yeah, okay. Anyway, right. So, far so good. And so far we have only, sorry, did anybody want to say something?
No, sorry, Lars. I just want to
No,
say,
no,
but
it's good.
you compiled only the data type function, but maybe I start really compiling the table sources. Yeah.
Until now, we have always done it like this. So module, name of the module where, and this exports everything. Okay, so I mean table. So if I go back to this data type function thing, I should also close the REPL, by the way, and reload, because I changed the Cabal file and the REPL doesn't automatically pick that up. So you have to close it and reload again. And let me load this data type functions module again. So now if I ask for information on table, it's not in scope. And the reason is that table is now defined in this model here, but I am now in the REPL, I am in this one. So these definitions that we did are, I mean, by default, they are not available in the whole program. They are, I mean, that's the point of modules, that you have to explicitly import something if you want to use that. So I could, and if I want to do that, I could write import here, import table, for example. So that's now maybe it was not a good idea to give that the same name, but doesn't matter. So this is the name of the module, not of the type. So I'm now importing into my data types function module this table module. And it's only complaining here because I'm not using it. But let's ignore this. And now if I reload here, so now it knows about table. So that's how you can import definitions from other modules into a module with import. Okay, that's good. And but now there is like, I mean, one problem is that this is very implicit. I mean, I could now do stuff like, I don't know, okay, I mean, this is because I'm using this type synonym for, I mean, type to define this tables here. This is just another name for list. So my tables are just lists. So for example, I could do stuff like reverse a table. So we had this table before this one. Sorry. Let me just make this annotation that I don't get the warnings. So this was our example table. And now I could do stuff like reverse of this table. Because, I mean, it's just a list. So all the functions on list work for this table as well. But this is a bit, I mean, dangerous, because I mean, it's supposed to be a table, not, I mean, it is a list, it's implemented as a list. But if you look at it as a table, then reverse doesn't make sense. So you don't really want people to reverse tables. They should only be able to use the API that's defined. So I mean, first thing, by the way, is we can do what we could do. We haven't seen that before. So if you don't, I mean, if you do it like we did before, everything, every top level definition in your module is exported. So if I import it here, this import gives me access to everything we defined here. You can also have so-called explicit export lists. So I can list what's in here. So I could say table, empty, insert, delete, lookup. And now, of course, there's no difference because I'm exporting everything anyway. So let me just load. But now, for example, if I ask for the type of delete, so it knows it. But if I don't export the delete here, and now if I reload, then it's not in scope any longer. So you can basically hide certain things and not export them. So then they are sort of private only to the module. So for helper functions or so, that's often used. Okay, so far so good. So I'm exporting these things, but because everybody, I mean, because it's still a list and just a type pseudonym for lists, I can reverse tables. And that is bad. And what is also bad is, I mean, my intention is that people use this API. So I can publish this in Hackage and say, look, I have a great new package for you where you that implements lookup tables, and you can use these things. Now the first problem is that because people see that it's lists, they can just also do things I never intended them to use on these tables, like a table. And the other thing is, maybe later I listened to a lecture on data structures, and I see that it was a silly idea to use key value lists, and I should use whatever red black trees instead. And I want to change the implementation of my tables, but still expose the same API. So I just want to make an implementation optimization. Now, because everything is out in the open, people maybe rely on the fact that I'm using lists. And then if I want to upgrade to a better implementation, then every code that uses my stuff breaks. So, and often we don't want that. So what can you do in such a situation? And this brings us to the next topic, next new type. So there is a thing, so we have seen two ways to define new data types in Haskell, yes, until now. Data and type. So data defines a completely new type. So you can give one or more constructors with arguments, and it defines a completely new type. And the type keyword we have seen is the second option, which just gives another name, a new name to an existing type. But it's really just a new name. So all the stuff you can do with the existing type, you can also do with a new type. So in this example, I can reverse a table because I can reverse a list. And there's a third option in Haskell, and that's called new type. And in principle, the syntax is the same as for data. So I must give a constructor. So I can, for example, call the constructor also table, though that's maybe a bit confusing, but nevertheless, I mean, people either call the constructor the same as the data type, or sometimes they also call it MK for make table. So, and this new type is like data. So it's like data with one constructor that takes one argument. And this is the case here. So I have only one constructor, this table constructor, and it has one argument, which is of type key value list. So now I get lots of errors because, I mean, the empty list is now no longer a table. Now I need the table constructor. So I must apply the table constructor to the empty list. Same here. This T is now a table and no longer a list. It makes no sense to const something to a table. I can only const to a list. So what I need to do is I pattern match here on the table constructor. So now this T is actually a list. So now I have this element that I const to my list, and I apply the table constructor again to the outside. So it's basically, I mean, it gets uglier. The code gets uglier. But we will see why we want to do this soon. So here again, I must match on the table constructor and here as well. Sorry. Table. There I have a problem now because, sorry, so this is fine. Now I can delete, but this is now again table. So I must somehow, okay, sorry, let me let me first fix everything else that we can concentrate on that. So let's leave this for now. Table. Table. So now everything is almost fine except for this. And what's the problem here? So the axis is a list of key value pairs. So the first case is fine. By applying the table constructor, I get a table again, and then I can delete from a table. So that's fine. Now in this case, I mean, of course, I need a table constructor on the outside. But the problem now is, I mean, so the axis is this list of key value pairs. By applying the table constructor, I get a table from which I can delete the key, the K. But now I want to get the list again, so that I can cons this this pair. So I somehow need a reverse operation for this table. So I can get the, given a list, I can apply the table constructor to get a table. But given a table, I also need a function to extract the list. So that's easy to write. We can maybe call it get table. That's most people would call it get table or untable. So let's call it get table. So given a table, KV, give me a list of key value pairs. So this function is very easy to write because a table only has one constructor. So there's only one equation. So just like this. And now with this get table function at my fingertips, I can solve my problem here, calling it here, get table. And now everything compiles again. Right. And let me just do this. Was there a question?
Yes.
So I got a question.
Yes.
So what is the difference between the data keyword and the new type? I mean,
I'll get to that. But so basically, in principle, you everywhere where you use new type, you could also use data. Not the other way around. So new type only works if there's exactly one constructor and that one constructor has exactly one argument. But in all those situations, I could also write, I mean, if I write data, then everything also compiles. So I can always replace a new type with data. The difference is efficiency. New types don't produce any overhead. So the compiler strips out this table constructor. So at runtime, basically, you are still working with lists. So it's just as efficient as if working with the original type. So it's just at the type level at compile time. So it's just so at runtime you don't pay a penalty. Whereas if you use data, then there is one additional layer of indirection, so it would be slightly less efficient. So that's the difference.
okay. So it is better to write this new type. Use this new type when we're using like other data structure that is already in the
Yes, whenever you can, you
standard,
should use.
right?
Yes. No, I mean, or it doesn't have to be in the standard. Also, I mean, it could also be one that you have defined. But whenever
Okay.
you define a type that has one constructor and one argument, one constructor with one argument, you should always use U type. And I mean, if I try to use data, then it's fine. It still compiles, but I get this warning: use new type instead of data.
Okay.
Right. Okay, so now if I do it like this, I haven't really, I mean, first of all, this is like horrible, right? I mean, or not horrible, but it's ugly. I mean, it's ugly because everywhere at certain places, I now had to put this ugly table constructor, and can make it a bit nicer by formatting again properly. Oh, sorry. anyway, so I mean, it looks as if I haven't gained anything and just lost. So the difference is now, and I mean, if I do it like this, then I really haven't won anything. By the way, this syntax, that means that I'm not just exporting the table type, but also all its constructors. So now, I mean, I still can, I mean, if I do it like this, then I still, I mean, one nice thing is that our code, I mean, oh, okay. I can almost also do it like this. Just not showable anymore. So let's do deriving show. Right. So if I use exactly the same code, I mean, this is now, I'm still in this data types functions module in my REPL. So this is now, you can think of this as a user of this library, of this new mini library table. So for users can still use the old code. So that's good, because I mean, this only uses the API. It only uses empty inserts, empty and insert. So this still works. And what's also good, if I do, sorry, just this reverse thing, that doesn't work anymore. So that's also good, because it's now no longer a list, it's now a table. Before, it was just another name for list. Now it's actually a different type. So the difference between new type and type is just another name for something. And new type really defines a new type that the compiler considers as a different type. So now I can't reverse my table anymore. And it says, basically, you can't, I mean, I want to reverse a list, but I have a table. So what's up? It's good. What is not good is that if I really want to, I could still get to the underlying list. So if I do, I mean, I can't reverse the table directly anymore, but I could use this get table function and then reverse. So the point is, I mean, it's still, the inner implementation details are still exposed to the user of the library, and he could somehow rely on that, and then it's difficult for you to upgrade to a better implementation. So this particular problem is easy to solve. I can just remove this get table from the export lists. So now I can't do that anymore, but I could still define that myself. So I could now in the REPL define get table access, and now I can do it again. To prevent that, I can also not export the table constructor. So if I do this, the type table is exported, but not the constructors. So if I now reload and try this thing again, so it doesn't know what get table is. If I try to define it, then it says the table constructor is not in scope. So by basically, so the idea is so that's a so-called abstract data type. So I mean in the module where I'm defining it, it's a very non-abstract data type. It's very concrete. It's just lists of pairs. But for the outside world, for a user of this type, now all the user basically has access to is the type itself, not to the constructor table. So it can't like get to the underlying list. And all the users of this module now can do is use those 4 exported functions, empty, insert, delete, lookup. So that means if later I swap out this implementation and use something like red black trees, then that and still provide the same API, then no client code basically will break, because they only can interact with this table type via those 4 functions. So that's a quite common technique that's used to implement abstract data types. So, for example, the actual implementation that one would use in these situations for key value pairs, maps of key value pairs, it's in the container package on Hackage. It's called map, the type, and it has a very similar API. I mean, much more, but in particular those 4 things it also has with very similar basically identical API, but a much more efficient implementation. And that also doesn't expose the implementation, at least not easily. So you can only interact with this type via the exposed API or interface. Right. So new type somehow enables that. And that's all. I mean, that's the 3 ways to define new data types. So the data constructor is the most general. I mean, not constructor. The data keyword is the most general one. So you can define arbitrary types with arbitrarily many constructors, and the constructors can have arbitrarily many arguments. Then the second way is type, which just gives a new name to an existing type. But wherever you use the new type, this is now, I mean, so if you use type, then whether you use the new name or the old name doesn't matter. You can basically exchange them everywhere. And everything you can do with the one, you can do with the other. It's really just a different name. And new type is sort of like, almost like a mix between the two. So it's like type in the sense that it basically just wraps the existing type. But it's like data in the sense that it defines a new data type. It doesn't just give a new name to some existing thing. It defines a new data type. And therefore but I mean, it does have this type aspect, so it wraps an existing type, and that means it has exactly one constructor and exactly one argument for that constructor. And then, as I answered to the question before, Haskell has special support for this, so it's more efficient. So when what the compiler does, it will basically remove this table constructor everywhere. So at runtime, the runtime representation of this table type now and key value pair list is exactly the same. So at runtime, this distinction would go away. So the table would be removed. So you pay no penalty in performance for using new type. So what you gain is like safety, that you don't do stuff with tables now that because they are lists that you don't want to do. So the compiler now makes sure that you only basically use, I mean, that you don't confuse tables with lists. Right. And let's just see what else was here to say. Oh yeah, one last thing. I defined the annoying get table thing, and that's a very common thing you want to do. I mean, the table constructor gives you a way to take a list and turn it into a table, but very often you also want to go the other way around. I mean, new type is basically, I mean, it's wrapping an existing type. So tables and lists of key value pairs are very closely related. I mean, every table is just like a wrapper around a list of key value pairs. So very often you want to go in this direction. So very often you would want to define a function like this, like get table. And therefore there's a special syntax in Haskell to do this automatically. So you would write curly brackets around this and then the name get table here and like this. And then you can remove that. And you basically get exactly the same. So my code still compiles, so this is still defined. Yes. So often you would do that. So basically this is the way to construct a table from a list, to wrap and to unwrap. So wrap a list to make it a table and unwrap a table to get to the list. And you can or cannot export that. So if I do this, then users of this library would have access to the get table. But if I just export the type, then not. So this is basically exactly the same as before, except that I didn't have to write this function by hand. Let me just see whether I have. Okay. So I explained new type. We did this constructor functions on tables. I didn't say that, but I mean, this follows. It's the same that we had before. standard design pattern on functions. So functions with two constructors tend to have two equations and so on. So in this case, there's only one constructor. So the pattern would just use this constructor and that's exactly what we did here everywhere. And what else? So I explained all that. So new type only works for one constructor that has one argument, except apart from that, it's exactly like data. But at runtime, it is guaranteed to have the same representation. So data is much more general, arbitrary number of constructors and arguments, but it introduces a small penalty at runtime. And I think this I already explained everything. So this slide just explains how they basically hit the implementation from the outside world. So now I'm free to optimize my library and pick a different implementation, and people interact with it via the API, the interface I provided. And let me just see what's after this. Okay, there are 3 more examples. So maybe we should we have another break? Or maybe let me just see whether it's are there questions? Let me first ask whether there are questions.
Not so far. And we have a bit less than an hour.
Yes, I know. Maybe I can do the transactions and we can have a short break and then do the other two.
Yeah,
I
sure.
always want. Okay, transactions. Let me just see. Yes. Okay, so seeing as this is a Cardano developer course, we want to do some like financial examples. So hence these transactions. So right, the idea is a transaction, and it's just a toy model. So the idea is transaction transfers some amount from one account to another account. And amounts, for simplicity's sake, are just ints, and account for the time being is just a string. And so we only have one constructor that's called transaction, and it has 3 arguments. So in particular, we can't use a new type because new type works if we have one constructor and one argument. So here are 3. So it must be data. And the type of the transaction constructor, so it takes an amount, an account, and another account, and constructs a transaction. And then, of course, if you want to define functions on transactions, because there's only one constructor, we will normally only have one equation, and then we pattern match on the 3 constructor arguments. Not sure whether I need to write this. Was it amount, account, deriving? That should not be here. Do this here. Don't want to pollute the table stuff. Show and eq, okay, and amount is int, type account is string. Okay, so far so good. And okay, now, somehow in order to work with it, I can write these accessor functions here. Tr amount, tr from, tr to. And I think I really don't do that now. So in order to, for example, extract the amount from a transaction, I would pattern match the transaction. So transaction ABC or AFT, and then just return the A. And I don't care about the from and the to, so I can use underscores. Same if I want to access the from, then I can again define a function br from, pattern match on transaction, the 3 arguments to the constructor, don't care about the first, don't care about the third, return the second. And same for tr2 if I want to extract the third argument. And this is a very common case, and it's very tedious if you always have to write these things. Therefore, similar to what we just saw for tables, there's so-called record syntax in Haskell. So if you have a data type with one constructor, but one or more arguments, then you can use so-called record syntax. So the syntax, and that is the same as we used for table. So the table that was just a special case was also record syntax. The only difference was there was only one argument. So now I have 3. So now the syntax is, again, you put curly braces around, and now you can give names to those 3 things. And I mean, on the slides, it's true mount, true from, true. So the syntax is like this. Sorry. And then they are separated by commas from. I mean, you can write it like this, but I normally like format it like this. But that's also a matter of personal taste, I suppose. Okay, I would format it like this. So what does that give us? So first of all, it works. I mean, it compiles. And secondly, you can still do the same thing as before. You can just use the transaction constructor and do something like 1000 Robertino Carina. Now we see, I mean, we derived a show instance here, and we see that now this somehow has an influence. So these names I gave to these so-called fields, the constructor arguments, are reflected in how GHD now implemented this automatic show instance. So that's one thing. Everything I can do before without this record syntax, I can still do. I can use the constructor. But now I don't have to define these tedious accessor functions, same as for table, where I don't have to define this get table. I now get that for free. So if I call this thing here, let's call it transaction TR. So that's my transaction. And now I automatically have this TR amount of TR. It's 1000 TR from Robertino, and TR2 is Carina. So that's so-called accessor functions. So that were in the slides here defined by hand when we didn't use record syntax. But they are now automatically generated by the compiler. So they are just normal functions. So you can ask for the type, for example. The type says, okay, given a transaction, it extracts this, I mean, gives me an amount. And similar for TR from and TR2. So that's cool. It automatically defines these so-called accessor functions. And it also, record syntax also comes with 2 more things, or at least 2 more things. So we saw how to construct a transaction. I mean, we can just use the transaction constructor and the arguments. However, now there's also a nicer or different way. So this transaction that I defined in the REPL, I can define it like this. Like I did in the RECL, but now I also alternatively can use so-called record syntax to construct this. And then the syntax is, instead of the colons here, I have equal signs. So to give the same transaction that I did in the REPL here, I could do it like this. I can reload. And I did exactly the same. And the order here doesn't matter, so I could also order them differently when I define the transaction. This is, of course, more verbose than just writing transaction 1000 Robertino Carina, but it's much more readable. And you don't have to remember the the order of the arguments. I mean, if we go with this original definition, it's not clear. I mean, there are these two accounts, but which is which? I mean, in this case, it's probably relatively obvious that that is from and that is to, but from the types you can't see. And so this is nicer because now we have names for the things, and you also don't have to remember in which order they came, because you can just, I mean, it doesn't matter. You could also here, I can just as well swap the two, and I still get the same. So that's, especially if you have many fields in your constructor, that's very useful. And this is a very common case. I mean, especially if you do anything, I mean, if you do anything like real world serious in Haskell, like anything related to business or also to Cardano and blockchain. I mean, these so-called record types, so types with one constructor and many fields, are all over the place and very common. I mean, you can think of a person type that has a name and an age and an address and a phone number and so on. And so this is very common, and therefore Haskell has this special support for it with this record syntax. It doesn't really give you any special new power, so you still can't do more than you could before. I mean, they are not like a new type of data types or anything, but it just makes it easier to the tooling easier, because I mean, you don't have to write so much, so it removes boilerplate. One last thing you can do is so-called record update syntax. So I think there's probably an example. Sorry, no, there's none. So let's say I mean, a stupid example. Whatever. It's just, let's just call it foo. So yes, I want to take a transaction and let's say just double the amount. Say double amount. So I mean, so I want to turn this, for example, into one again with Karina and Robertino, but instead of 1,000, that should then become 2,000. So of course we know how to do that, I hope. I mean, one way would be to do transaction amount from 2 and then define it as transaction 2 times amount from 2. Right? Perfectly fine in this example, maybe also good. So if I have my transaction, if I have double amount, then it's the same, but the amount has been doubled. However, with record syntax, there's an alternative for this. We can also write it like, sorry, let me just show you again. What is typical is, or often we have some functions like that, where basically most of the fields are untouched. Like in this example, the F and the T, we keep the old one, and we only modify the A in this example. And because that's such a common case, there's this so-called record update syntax, and that syntax is as follows. And I made a mistake. No, I didn't. Because sorry, TR is, I can't call it TR because this is my TR. Let's call it T. So this is so-called record update syntax. So T is the input transaction. So this is the same T. And now in curly brackets, I can give values for certain fields, but not all of them. In this case, I say, okay, the result of this function should be as before, the old T, but I want to modify the amount field. So I take the amount of the old T and multiply it by 2. And I'm not mentioning to and from here, so therefore the to and from will be the same as in the T. So that's the so-called record update syntax. Right, and yet So let's say we want now use our lookup tables. That we defined before to basically simulate a bank. So we have a bunch of accounts. We model them as lookup tables from account to amount. And now we do process transaction. And this is like horrible, but anyway. Okay, fine. So the idea is, given a transaction, how do we update the accounts? So process transaction. Just don't have to be consistent with the AS, fine. So on the slides, he actually doesn't use record syntax. So maybe in this case, it's actually easier to do it like this. Right. And so now what do I need to do? I must look up, I mean, how much from has and how much to has, and maybe they don't have accounts yet. And then I must, I mean, subtract this A amount from and add it to 2. So as a first step, I would like to know how much money from and to actually have. And I could do all of that inline, but I mean, what I really would like to know now, is have like some intermediate variables or temporary variables. So, and that's possible in Haskell. I just want to check what. So, and one way to do that is with the so-called let in construct. So it has a let and an in, and between the let and the in, you can define bindings. So they are then local just inside here in this let in block, and then you can use them in the let. So the idea is we define something like f old. So that's the amount that from has before the transaction, and t old. So what t has before the transaction. And then let me just see how to do it here. Okay. And then once we have it, we can insert. So for f, so what's the new value of from? That is the old value of from minus the amount we are transferring. And what's the new value of 2? Well, that's the old value of 2 plus the amount we are transferring into the accounts. I mean, this is like horrible because we don't check whether people overdraw their accounts and whatever, but I mean, it's just an example. And it's just an example to show how you can do this local variables or local bindings. Okay, now we of course have to implement it. So what is the old amount? I mean, we can do lookup. Lookup f in accounts. But if we do this, and here lookup t account. But now we get errors because we are expecting ints, but we get maybe amounts. Because remember, lookup can fail. Maybe f and or t don't have accounts yet, so they're not in this lookup table. So somehow, what do we do in that case? And the idea is to just use 0. And we, at the very beginning of the lecture, we defined, I mean, our first example was this from maybe, which allows us to use a default value. So if the maybe is a just, we use the just, but if it's a nothing, we use the default value. So this comes in handy now, so we can use that from maybe default 0. And this, and I mean, we can try an example. So let's say we start, I mean, our accounts are insert Robertino 5,000 empty. So that's, let's say, our start bank. And now we have our transaction. And now if we do process transaction, I must reload. I must do this again. Okay. So if I now do process transaction, this example transaction TR, my examples account. So then we end up with lookup table where Robertino now has 4,000 and Karina has 1,000. And now we could process another transaction. Process transaction. Transaction. Let's say 50. Karina has. And so on. Right. So that's this example. Okay, let's see what's the time. Okay, we have half an hour left. So do we want another break? I mean, a short one, 5 minutes or so?
Yeah, sure.
Yes.
Okay. Right. Then let's have 5 minutes break and then do the rest quickly.
Yeah.
Okay, should we do the rest now? Are there any questions?
Not so far.
Okay, then second to last example, binary trees. So that's also not built in, but I mean, trees, I mean, some point of view would be that basically every data type in Haskell is a tree, or most are. So there are lots of trees in various libraries and so on, but this one is like now for the lecture, but we will always come back to that as an example. It's a nice type. So the idea is binary trees with data of type A in the leaves. So, and there are two constructors. So a tree can be a leaf with a value of type A, or it can be a node that has two children, a left subtree and a right subtree. So that's the idea. Data tree A, either a leaf A or a node of recursively two trees. We can driving show, let's say. And it's always good to have an example. Let's say a tree int. So we can have a tree, let's say it's a node with two subtrees, and the left subtree is just a leaf, and the right subtree is another node with children that are leaves each. So let's do this. We have a node. The left subtree is just a leaf, and the right subtree, and let me just write this. I mean, with Haskell, you can always be creative with. I mean, I should probably have mentioned that before. So layout is important in Haskell. So there are no semicolons, but layout matters. So you can't. So things need to be aligned. But how you align them is sort of up to you. So I mean, I could write this in the same line like I always did, but in this case it gets messy, so I decide to do it like this. And I mean, I could also have that like here, example, but not there. So it must be indented from the top, from the definition. Anyway, so what did I say? Another node here where with two leaves as children. So I can have leaf 17 and leaf 8. Okay, let's then compile. Yes, so I can show it. So this would be, I mean, if you want to draw a picture, it would be so the node, the root of the tree, and then on the left we have the 42, and on the right there's another subtree. No, sorry. With the 17 and the 8, something like this. It's not a good picture. Sorry, I should maybe have. I don't want to spend too much time drawing pictures, but trees are important, so let's do it like this. Okay, like this. So that would be this tree now as an example. And so we have two constructors again, but so the one has both have arguments. The first one has one argument of type A, and the second one is recursive, but it's even doubly recursive because it called, I mean, it's the type we're defining the tree twice. So we expect functions on trees to have two equations, one for the leaf case, one for the node case, and we expect that somehow when we define a function that we will recursively call it on the left, in the node case, on the left subtree and on the right subtree. So one example function is flattening a tree to a list. So call it flatten. So tree A to a list of A's. So the idea is if we apply that to our exploratory tree, we would get the list with 3 elements, 42, 17, 8. So left to right order. Okay, so we need 2 cases, one for a leaf case and one for the node case. So if it's a leaf with a value of type A, well, then the list is just a singleton list, the list with 1 element, just that A. And if we want to flatten a node with the left and the right subtree, well, then we recursively call flatten on the left, and we recursively call flatten on the right. We get 2 lists, and we just concatenate them. And we can try it out on our example tree, and indeed we get the list 42, 17, 8. Okay. And another thing is the height of a tree. Another example. So the height is basically how the leaf furthest down, how far away it is from the root of the tree. So this 42 would sit at height 1. The root is at height 0. This here is height 1. And the 17 and 8 are at height 2. So in our example tree would have height 2. So again, leaf and node. So the height of a leaf, if it's just a leaf, it has height 0. And we don't care about the value at the leaf. And if it's a node, well, then we recursively call height on the left and we call height on the right. And now, so first of all, we must add 1 somehow, but we also, here we see these trees are not balanced necessarily. So if we do this here, then the height on the left would be 0, but the height on the right, the left subtree is the leaf, would be 0, but the right subtree is this tree, which would have height 1. So we must take the maximum of the 2, and there is a max function in Haskell that does just that. And now we must add 1 to the result. And if we do this and try it on our example tree, we get 2. So the right answer. And no. Okay, that's height. And I think there will be more examples of functions to define on trees in the assignments. So let's look at the last example. This is basically just an example to demonstrate, to have an example. Until now, almost all our types had either 1 or 2 constructors. So the idea is to just have a type that's a bit wilder and has more constructors. And until now, we have had, recursive data types, like lists where there was like 1 recursive occurrence. Now the trees had 2, and but it can also be more than that. So the idea here is, and that is something Haskell is particularly good at, things like this, to model expressions. So Haskell is particularly good, for example, to define new programming languages. They can define constructions in the language as Haskell data types. So this is a mini example of that. So the idea is that this export type represents simple arithmetic expressions. Could think of it as like arithmetic expressions in a new programming language that you want to define. So we have, let's do this quickly. So data export. So we have 1 constructor lit for literal. Sorry. Data export. So, okay, 1 constructor lit for literal, something like 7 or 42. So lit 7 or lit 42 would just be the arithmetic expression literally representing that. Okay, fine. a number, an int. So now we want to do addition. So we want to be able to add two expressions. So this is a recursive constructor with mentions the type we're defining twice. What else do we have? Okay. Then neg for negation. So want to negate an expression. It's also recursive, but only mentions expression once. And finally, just for fun to have something with 3, we also do an if 0. So the idea is gets 3 expressions, and the interpretation would be the first expression is 0, then the value of the whole thing is the second one, otherwise the third one. And can do deriving show. And now we can have an example expression. I'm sure there's one somewhere, maybe not. No, there's not. So let's come up with one. So I just informally write this, so it should be interesting. It should have something. So something like, let's call it X. So let's say we do if 0. Sorry, sometimes my editor does that. So if 0, let's say lit 42 at must count. Okay. Okay, yes. Okay, that would be an example expression. So the idea is, it's supposed to be something like if 42 plus minus 42 gleich 0, then 1 else 2, right? That's supposed to be this expression, sort of. Anyway, it's important to notice that, this is just a data type. It doesn't do anything. So, and we will talk about that as well more in later lectures when we talk about DSL and so on, domain-specific languages. So, you understand what I mean by this or what my intention for this type is, but it's just a stupid data type. It doesn't do anything. It has a priori nothing to do with arithmetic. I've used suggestive names for the constructors, but it has nothing to do with calculation. It's just a data type. But of course, we can put meaning into it by defining functions on it. And one function we probably would want to define is to evaluate an expression. So given an expression, evaluate to an int. And so let's write this. Let's call it eval. Given an expression, evaluate it to an integer. Okay, and now, again, this is supposed to be really boring for you now because I've repeated myself so many times the last hours and days. So the standard design pattern in Haskell for functions follows the types. So in this case, we have a type with 4 constructors. So we expect 4 equations. And because these 3 constructors are recursive, we expect those 3 equations to be recursive. And we expect this one to call itself recursively twice, this one once, and this one even 3 times. So, and eval now is an example for this. So let's do our 4 equations. So we have the lit case. It's a literal integer. We have the add case. We have the neg case. And we have the if 0 XYZ case. Okay, and now let's look. So how do we evaluate a literal where the n is an int? Well, that just evaluates to itself basically. to n. So how do we evaluate addition? And we already know from what I just said that these three will be recursive definitions. So we will recursively evaluate x and recursively evaluate y, and then obviously add the results. So we will eval x and eval y and add the results. Neg, I mean, we will recursively eval x, and then how do we negate that? I mean, this is a bit, the unary minus operator in Haskell is a bit of a pain. So I think if I just write this, not sure that actually works. It does, I think. Okay, fine. I could also write negate. So there is a function called negate. But I think in this case, I can also just use this. Let me just try it. I never trust the minus. I can't. Let's write undefined there. Let's try it. Eval neg lit 42. Yeah, okay, fine, that works. So now this case, okay, I mean, there are several ways to write that. I mean, one is to use if then else, but another would be to use guards. So we can write if eval x, so the first equals 0, then eval y else eval z. So that's good. I mean, we could also alternatively, so that's perfectly fine, but we could also use guards instead and say eval x equals 0. In that case, it's eval y, and otherwise it's eval z. Okay, and now we can try it out in our example expression, and we get 1, which seems to be correct. If I instead do something like this, so this would now be basically this. And we get 42. So 7 is not 0, so we get 42. So that works. Another, we still have 5 minutes, so I think the slides end there. But another example of a function would be a pretty printer or somewhat pretty printer. So basically like a show. So we could do pretty, which turns an expression into a string. We do pretty, and again, we have our 4 cases. So for literal, we can just show the literal itself. If we have at x, y, we can do we can start with parentheses, then pretty the first argument, then concatenate that with a plus, and concatenate it with pretty the second argument, and finally close the parentheses. Is that okay? Yeah, just warning because the compiler detects that I'm missing these 2 cases. So pretty neg x can do sorry. So I'm going overboard here with parentheses to So, I mean, if you wanted to do this properly, then you would somehow try to avoid too many parentheses. I just want to make sure that it's correct. And finally, the if 0 x, y, z case. For example, if x why does stupid stylish Haskell not indent? I don't know. Okay, let's see. Now we can try this pretty function on x1. Doesn't look too bad. And we can try it on x2. Right. Yes. So this is just an example of, I mean, as I said, that is something Haskell is used for a lot to define these, I mean, to basically symbolically be able to manipulate expressions and work with them. Especially if you're actually implementing your own programming language, then, I mean, compiler and so on, it's easy, relatively easy to write in Haskell. So that's typically something is called syntax tree. So you have all the constructs of your programming language, they get their constructors, and then you work with that. And I think actually Haskell itself is implemented in Haskell. So yeah. So there's a, I mean, the GHG Haskell compiler is written in Haskell. So it's actually very suited for stuff like this. And it gives a nice example that types can be quite wild. I mean, many constructors and different arguments, some constructors recursive, others not. So in this example, the last three are recursive, but the first one is not, and so on. Okay, so I think that's it. Are there any questions before we leave?
Seems that not so far. And so far it's the end of the lecture. So if you want to ask a question, you have to do it now or wait till Monday. I mean, you can ask in Discord, but it's not going to be live.
Right. And is there anything to say to the assignment? So now that I completed this lecture, I think we will release the second assignment, right? Or-
Yes. And then they will have an extra day because they will have the weekend to complete them. So the assignment is due Monday before the lecture.
Yes, and please let us know if you still have technical problems, like getting your environment working, or of course also other questions. Okay, if there's nothing else, nobody has a question, then I wish you a nice weekend, and then I'll talk to you again on Monday.
I have a question.
Okay, please
Is
go ahead.
the assignment on GitHub, are we doing from number 1 to from homework 1 to 15, or is just homework 1?
I think now in the beginning, for the first 5 lectures or so, there will be an assignment after each lecture. And then after that, we switch to a weekly rhythm. So then there will only be an assignment for every week, not for every lecture. But in the beginning, there's one for the first 5 or so, there's an assignment for every lecture. But
And-
they are,
and
I
they
mean,
are all
as
due-
compensation, they are also easier. So the later ones, the weekly ones, will be more difficult to solve. You wanted to
They
say?
are all due. Sorry, they are all due before the next lecture, so you don't have like a bunch of days. You have at most 2 days to complete them.
Right now, yes. And then in a week or so, we'll switch to this slower rhythm where it's only once a week you get assignments.
I have a question.
Yes.
Between the first assignment and today's assignment, which one have you postponed the deadline?
I think for
None.
the first one, because, I mean, on Monday, I didn't finish this introductory
right.
lecture.
Yeah.
So normally the first assignment would have been due on Wednesday already, but we shifted that to today, I assume, right?
Yeah, it was. I checked. It said the deadline was today at 9 o'clock. Is it still today at 9 o'clock or?
Yeah,
Oh,
it is.
And yes, and we're going to release the one that comes next. The one that is due on Monday is going to be released today, but that's the second assignment.
okay. Thank you.
Okay, any other questions?
Maybe I can add. In the first lecture, you said that there was no possibility of each of our assignments to be checked because we were too
Ah.
many.
Yeah, that's a good point. So now, seeing as we shrunk dramatically, unfortunately, yes, now you can just all do your own assignments. It's way better.
Yeah, it's way better. Thank you.
Welcome. No, I just saw the number in the beginning. It was like 150 people. Then we wouldn't have been able to look at every single one. But now, of course, we can. Or rather, my dear colleagues can.
Yes.
Sorry. Yeah, I hope it won't drop even further. Then we have to see whether we. But I mean, yeah, today we had like 20-ish people, so I hope it stays that way. Maybe over the weekend, some people revisit everything. Would be good. Okay, any other questions? Right. Okay. And if there are no more questions, so after the lecture, I think Robertino or Karina, you will publish. Oh,
yeah.
sorry.
Hello.
Hello. Hi.
Yeah. I think I have a suggestion here, please.
So you have a what? Yeah, go ahead.
This software, though the truth is, mostly after the training, we used to be given a kind of assignment one way or the other. But the truth remains, some of us, we are yet unable to get on how to set up this software on our device, because I expected this knowledge to be practical one. There is more to being abstract and being just following up theoretically on screen without practicing what we are really learning. So I think a step-by-step process of how to install all this software, then ways to get these program rights is what really matters here. Because I could remember very well the last programming language I did was just all this Fortran 90 and Fortran 77 in about 11, 12 years ago. And things are fast changing. I've been battling with my GitHub, though my GitHub account is almost, I think, some 7, 8 years old. Being a old cryptocurrency enthusiast who has been active in the blockchain and cryptocurrency space. But what we've been doing so far, I'm still finding it tough to get on. I contacted the program manager. I was told to have it calm and follow the process, which I know that though the beginning might be rough, but as time gets by with my consistent studying and thorough following up of the program tutor master, who is this last, I believe, and my own in-depth studies as well, I should be able to get along. So I think a good is not enough where better can be done. If there could be some additional tutor by people who are well grounded in Haskell Haskell programming language development, who can maybe once in a while who we can just contact, because even everyone I've been contacting, they're just telling me they are not familiar with blockchain development, coding and the likes. But but the fact is, I'm passionate about this. I must know this, and I'm ready to give it all in. So that is why I'm so curious. I've been consistent right from the onset, and but I just need something to ignite my passion the more, so I can keep the fire burning. So if there is a way we can be tutored, like, okay, my system now, I have my system, I don't have the soft, I'm unable to run the software. I register on Gitpod, I downloaded this what's the name of this Visual Studio Code. But the two assignments that has been given in the last two classes before this, I couldn't access any of them because training, the code and everything. I try to see possibly if I can be watching the video and be practicing what Lars has been taking us. Then gradually, these reference material that are being cited at the bottom of the introductory page, I believe with those and the video, I should be able to at least learn one or two things. I know it might not be a speedy process. The beginning might be rough, but as I'm not getting along at all. I must confess that. So I need you guys, I need your touch, as in your improvements on that.
Right. Toby wants something to, or Becky, Toby, you want to say something? You raised your hand.
Yeah, good afternoon. Yeah, just to speak to what David has said. Actually, personally, I have background in Python, but I discovered that Python is an imperative language, while Haskell is a functional language. So, based on what David has said, if there's something that can be done so that we could, because every Wednesday, every Monday, Wednesday, Friday, it will be like another extra 3 hours. If you miss it, where are you going to start from? It's something personally I'm also passionate about, but the clarity is not been that clear. And I believe that if there's any other way to simplify it, like Haskell for using this word dummies, because I've seen different books like that, so that we can quickly get along and match up with the piece. And at the end of the day, the investment of time and resources will not be wasted. So definitely appreciate that.
Okay, I mean, for what David said, I mean, it should be just a matter of clicking on the link as I showed you in the beginning. So in principle, you don't have to install anything on your machine. I mean, I know that some of you struggled. I mean, as I said in the beginning, I also struggled myself for some reason with this Gitpod, but that's the easiest. Then you don't have to install anything on your own device to just open this. I mean, that's the easiest. Then you just need a browser. So then I think for you, the best would be if you could get that to work. And I mean, it's difficult to reproduce. I think for Robertino, for example, it just works, right? For most people, it just works. So,
Yeah.
or I mean, for me, as I said, I was also struggling. I was stuck in this authorization loop. So for me, it helped to delete my Gitpod account basically and create a new one. But I'm not sure whether that would help for everyone.
And there are also, I mean, if in the repository we have as well, like linked in the instructions of installations, you can either have the remote development environment, which is the easier one, Gitpod. You can also have the local development environment, that is the one that Lars uses in the lectures. And we also have this third option of installing things on your computer. And I linked a video where I go step by step through the installation process, so that you have like these three options. Maybe you can cycle through them to see if one of those function, or which one you go far enough, or you have a specific enough issue that we can help with.
Right. I mean, we trying to think. I mean, we could also take 1 hour or whatever I mean, it's difficult. For the last course, we were like physically in Nairobi for 2 weeks, so we could assist with things like that. Now, of course, it's more difficult, but maybe we can set aside like an hour or so next, or an hour, I don't know, on Monday, to if people still can't get it to work, to basically help them. I'm not sure what the best way would be to get everybody a working environment.
Yes, maybe Anderson can support us. Maybe the people have a problem, still have problems with the environment. Could send some, I don't know, a screenshot of the error they have in the different environment they try it to look in, to support in these or useless, but have the all resources before support the old people. Yeah, maybe.
Yes. So that's one thing we can do. And then, of course, I mean, maybe you can also help each other. So we have these channels. I hope start some of to work. So maybe you can. Oops, that didn't.
Lars, I think we're losing you a bit.
Sorry. No, I wanted to say maybe you can also help each other. So, I mean, hopefully most of the in the class have managed to set up the environment. So maybe they can also try to help the others that don't. So if you just post on Telegram, for example, screenshots, as Karina said, with your problems, then maybe you, others can also help. And of course, if we can do anything, we're also happy to help. It's sometimes a bit difficult, of course, with, I mean, for Robertino, it just works. You click on Gitbot and it just opens. So these things are sometimes a bit tricky to sort out. But of course, we'll try. And as for Haskell and Python, I mean, that is like normal that people that come from a different programming language struggle with Haskell in the beginning. That is, I mean, everybody experiences that, or most people. So all you can do there is to just try to do all the assignments and practice a lot, I think. And we can put this link to this Learn Your Haskell for Great Good. Maybe we can put it on the GitHub repo in the README as a reference, or other references. I mean, we can also put a link to your course, for example.
Yes,
to your-
both are already in the
okay.
bibliography. So yeah.
And so let me just see briefly. Let me just share quickly again.
I can share them if
Okay. Do you want to? Or?
Oh, yeah, both
Sorry.
are fine.
Okay. Let me just. So
Then,
this is.
yeah. Okay. Can I say something, please?
Of course. Let me just. Sorry, just 1 second. Just wanted
Alright.
to.
Cardano Dev 20. Yeah.
Is that the right one? The right link?
I think it's the 2024. Karina, which one did we?
Yeah, no, it's not the one I sent.
I mean,
you.
that one's that private, so it's the other one.
It ends in 2024, so maybe you can filter
This
with
one,
that.
Yeah. Right. So this is the basically homepage of the class. And then, right.
The first two
So,
links are the.
Yeah, this is the book I was recommending on Monday, I think. That's
Exactly.
also exactly. So there's the link. And as I said on Monday already, I mean, you don't even have to buy it. It's available online. And then this link here, it's Robertino's course, right?
Yes.
Basically. Yes. So this is a YouTube video series that we did also to introduce Haskell. I think it doesn't go as deep as this one does, but for that it's very leisurely paced, right, Robertino?
Yeah, exactly.
And the idea is to basically teach you what you need to do Plutus. So if you are mostly interested in doing like D-apps on Cardano, that is also good. So if you want to see Robertino explain it slower than I have time for, then this is also a good link. So there are lots of stuff there as well.
Those
YouTube
are like
videos.
interactive development environments and the videos as well.
Mm-hmm. Right. So there are just on the homepage resources. This one is also a book. It's somewhat outdated, but still, I mean, used to be one of the best Haskell books. But this is more. I mean, as the name suggests, so it's not strictly an introduction. And yeah, so there are books, and then later for Marlo and Plutus as well, of course. Yeah, so I also don't know what else to say with the environment. But I mean, hopefully one of the three. Where is this? What you said with the walkthrough? Where's that link?
Yes, right there.
Yeah.
There. If you want to run examples, yes, those 3 bullet points are the 3 options. And the last bullet point has this link that says these instructions, and that's a video that is called step by step installing GHC app, and then GHC and blah blah blah.
Yes, so there Robertino goes. I have to watch the ad first.
Yeah.
Right. So anyway, that's Robertino explaining in detail how to set everything up if you want to use this third option. So the easiest would be this one. You just click on the button like I did here. And you just click on this button and then you have your environment. I just clicked on this open in Gitpod button, and then I don't have to install anything on my computer. But then there are these 2 other options where you have to install something on your computer. So in this case, you only have to install Docker and VS Code. And for the third option, it's basically the fully local one where everything locally. There you also have to use GHC up to install the GHC compiler, and that is all explained in this video.
Yes. And so if someone use Nix, we also have the old instruction to use Nix to run the old environment. So, yeah.
Is that also somewhere here?
No.
Okay.
No, I just say.
Right. Yeah, so if somebody wants to do it with Nix, then you can contact Karina and she can help you with that.
No, we can put the link into the README, but it's only the 4 option to do that. Yeah.
Yes. Okay. Yes, so hopefully one of 3 or 4 options will work for you. Okay, is there anything else?
So Lars, what you're trying to say in essence now is these what to call it, this app I downloaded on my PC here, these what's the name, okay, Visual Studio Code alone is sufficient for me to run this programming language, to run these okay.
I mean, you don't even have to use Visual Studio Code if you go with the first option. You just need your browser. But you can, I mean, if you have Visual Studio Code, that's also sufficient. If you have Docker and Visual Studio Code. So as explained in this bullet point.
Okay. Then do you have a soft copy of these this textbook that we have the web link? Can we get a soft copy that we can just that we can save on our device and be using to be studying, or we just have to go to, is there a channel where we can buy, or it's until when we get to the web link that we have to click on the link and have to read it? Or what do you suggest? Can we get the copy, since you said the book?
I mean, I don't have it. You mean if I have a PDF? I don't. I mean,
Yeah.
I have the book in paper, and then there's the website, but I don't have a PDF, I think.
Okay, but is it common in library? Can we get in library, or can we buy it? Where can we get it to buy?
Well, it's on. I mean, I think you can buy it right there on the website. I just don't know whether they deliver to you. It happens to be No Starch Press, actually. um,
I mean, but you can. I just open it, and you can buy a PDF if you want.
oh, you can? Oh, okay.
Yes.
Where's that? Is that if you click
If
on
you
buy it?
click on the buy, yeah.
Okay, I think that will be okay. Thank you very much.
Although you could like download the HTML and run it locally. I mean, if you maybe there's an extension, but I mean, you could download the actual HTML of the website and just have it without internet, but you will have to like figure that out.
Okay, I will check that. I will look into that.
Okay.
Look into that. I really appreciate it. Thank you very much. So let's go and get that done. And if there's anywhere we have concerns, we will definitely get back to you guys on it.
Yes, please do.
Yes, yeah. Happy to help always. Yeah.
Thank you very much.
Okay, anything else? Okay, then thank you, and have a nice weekend, everyone, and then I'll see you on Monday.
You too.
Thank you. Nice
Thank
weekend.
you.
Bye bye.
Bye-bye.
Bye.
Yeah, bye.
You.